Good evening, welcome back. This is step 1994, or step 1, 1994, question number 4. So there are two parts of this question. First one is sort of us deriving this sort of trig identity that 1 minus cosine alpha divided by sine alpha is just tan alpha over 2. Tan of alpha over 2. So alpha over 2 is in that sort of input to the tan function. So we have to sort of derive that identity. We have to show that it's true, verify it, right? Effectively go from start from the left-hand side and show that's equivalent to the right-hand side. And then after we do that, we have to basically just calculate an integral, right? We need to calculate that definite integral on the bottom. But they've given us an indefinite integral on the top to help us calculate that definite integral on the bottom. So actually it might not be too bad, right? This question is quite bad when you look at it for the first time, but then you realize that actually sort of half of this is just them giving us some result that we need to use. And then if you actually look at the result with a little bit of sort of intelligent thinking, you can realize that actually what they want us to to show is very similar to the thing they've already given us with a couple of changes, right? So actually, this question ends up being not too bad for that reason, right? You don't actually need to do too much. They've given us a lot of stuff here to work with. So let's just get straight into this. Okay, so let me get on the board here. Sorry, I realized I started this video and I wasn't even on the board. Give me 2 seconds here to get on the board. Okay, come on. Step 1994. Sorry about this. You can just 2 times this bit. I'm just getting on the board here. Okay. Here we go. So, let's get started. So, I guess we should do this chronologically. So, let's start with part I. So, I mean, the first thing I'm going to consider is, actually sort of seems slightly unrelated, but actually isn't when you think about it, is sine of 2 alpha. So, we definitely know what that is. We know that sine of 2 alpha is equal to 2 sine of alpha cosine of alpha. So this is our double angle formula for sine, right? And you can derive it with your compound angle formula for sine. So sine of alpha plus beta. So that is another formula in itself, which I won't go through. But that's how you can derive sine 2 alpha, by just letting beta equal alpha. So effectively what you get in that formula is that's equal to sine alpha cosine beta, add cosine alpha sine beta. And so what ends up happening when you let beta equal alpha is you get this is just equal to sine alpha cosine alpha, add cosine alpha sine alpha, which is clearly just 2 sine alpha cosine alpha, right? So that's how you can derive it. And if you're wondering how to derive this compound angle formula, then you can do it geometrically. But again, that's actually slightly longer, so I won't do that here. But if you have that there, if you can derive that, if you can accept that, then you can also accept that sine of 2 alpha is 2 sine of alpha cosine of alpha. Right. So that means that if you give me some alpha, then I can tell you what sine of 2 times that alpha is. Equivalently, if you give me some alpha, right? If you give me some alpha over 2, right? I can also tell you what sine of alpha is, right? Effectively, if you give me sine alpha, if you give me alpha, I can clearly tell you sine of 2 alpha, since I just use this formula, right? I just do sine of that alpha, multiply it by cosine of that alpha, and then multiply that by 2. But equivalently, if you give me alpha over 2, I can tell you sine of alpha, since that is just the same as sine of 2 times alpha over 2, right? Which ends up being 2 sine alpha over 2 cosine alpha over 2. So if you give me some alpha over 2, I can tell you sine alpha by doing sine of that alpha over 2, multiplying it by cosine of that alpha over 2, and then multiplying it by 2. So sine alpha in general is just 2 sine alpha over 2 cosine alpha over 2. So I'm going to box that. So that's a result that you should be able to accept if you want to prove that sort of first statement. So sine alpha is 2 sine alpha over 2 cosine alpha over 2. Okay, so let's box that up. Nice. What about 1 minus cosine alpha though? What is that? Right, well, we definitely know, so we also know that cosine of 2 alpha, so I've thought about sine of 2 alpha, what's cosine of 2 alpha? That's 1 minus 2 sine squared alpha, right? So this in itself is another identity, double angle formula, cosine this time, which can just be derived by considering again the compound angle formula for cosine. So if you know what this is, you can let beta equal alpha and go to this, right? And again, deriving this is can be done geometrically, and I won't do it here. But if you can accept that the cosine of alpha plus beta formula is correct, then you can also accept that this formula is correct. Okay, so if I have cosine of 2 alpha, that means that if you give me some alpha, I can tell you what cosine of 2 alpha is, right? But also, if you give me some alpha over 2, I can tell you what cosine of alpha is, right? Because again, cosine of alpha is just cosine of 2 times alpha over 2, right? So, and that is just 1 minus 2 sine squared of alpha over 2. So if I rearrange this, then what you notice is, and just sort of moving down here, that 1 minus cosine of alpha actually just ends up being 2 multiplied by sine squared alpha over 2, right? So that's particularly elegant, because now, instead of sort of just using 1 minus cosine alpha and sine alpha in our fraction, we can use 2 sine of alpha over 2 times cosine of alpha over 2 and 2 sine squared alpha over 2, right? So with this, so our fraction becomes, so 1 minus cosine of alpha divided by sine alpha, that divided by sine alpha is just the same thing as me doing 2 sine squared alpha over 2 and then dividing that whole thing by 2 sine alpha over 2 cosine alpha over 2. Right, so that's looking pretty promising there. Because, first of all, I have everything in terms of alpha over 2, so there's no sine alpha and sine 2 alpha in there or whatever. So everything's in terms of sine alpha over 2, but to be fair, that was true in the sort of first case as well anyway, because everything in the first sort of on the left-hand side there is in terms of alpha, so there wasn't any alpha or alpha and 2 alpha that I had to deal with. It was just all in terms of something of alpha anyway, so it wasn't really, the fact that it's in terms of alpha over 2 doesn't really mean anything by itself, but also we can cancel things here, right? This 2 cancels with this 2, and one of the signs will cancel out, right? So what I end up getting is effectively that fraction is just the same thing as sine of alpha over 2 divided by cosine of alpha over 2, right? And cosine, or any sine of x over cosine of x, is tan of x, right? And in this case, x is alpha over 2. So we therefore have shown that 1 minus cosine alpha over sine alpha is indeed tan of alpha over 2. Okay, so that's the first part of the question. I guess let's just go back over here to the sort of the other side of the question, and let's have a look at the second part of the question. Well, we're asked to sort of show that if 0 is less than alpha is less than pi, then that integral is equal to a half times pi minus alpha. Okay, that integral doesn't look particularly nice, but let's have a think. Okay, so that integral is the integral from 0 to 1 of sine alpha, right, divided by some quadratic in x, right? So 1 minus 2x cosine alpha add x squared. So we're doing an integral of all that with respect to x. Okay, that looks very daunting. And, you know, I would find this pretty tricky if I didn't see that clue that they've given us, right? Because that clue, 1 over 1, the integral of 1 over 1 minus 2kx plus x squared, looks very similar to what they've given us over here. In fact, it's pretty much the same thing. If I write it like this, if I write my integral as sine alpha multiplied by the integral from 0 to 1 of 1 divided by 1 minus 2x cosine alpha, right, add x squared, right? So this is actually just the same, and of course, with respect to x, this thing here is just the same as the integral they gave us, except k is equal to cosine of alpha. So they've given us this result, so 1 over the square root of 1 minus k squared arctan of x minus k over the square root of 1 minus k squared, plus some constant c, right, because that was an indefinite, but we won't need to worry about any constants in R1 because it's a definite integral. And so in effect, since they've given us that result, we can basically just use that with k equals cosine alpha, right? Because that's a constant with respect to x. So it's perfectly fine to just, you know, take the answer that we had for the indefinite integral and evaluate it from 0 to 1 with k being cosine alpha, right? Okay, fine. So let's do that. And of course, also notice that it says if the mod of k is less than 1, well, the mod of cosine alpha is strictly between minus 1 and 1. So the mod of cosine alpha will most of the time be less than 1, except on that sort of, on the points where it is 1. But if we think about this inequality here, so 0 is less than alpha is less than pi, we notice that cosine of 0 is 1, and it's not including that point. And so it's going to go 1, 0, minus 1, and also cosine of pi is minus 1, but it doesn't include that point either. So the mod will never be 1, so that's fine. We can do this. So that's good. So k is equal to cosine alpha. So I guess let's plug this into what sort of the I guess result they gave us. So this is going to be equal to sine of alpha multiplied by 1 over the square root of 1 minus cosine squared alpha, right? Because k is just cosine alpha. And then multiplied by arctan of x minus cosine of alpha. And then that all divided by the square root of 1 minus cosine squared alpha. Once again, k is just cosine alpha, right? And because it's definite, we don't need the plus c. You can put it in there, but it will be cancelled out, right? So in fact, all we're doing is we're just evaluating this from 0 to 1. Okay, right? Because it's a definite integral. So, and again, I could just put the plus c, but then I'm going to have plus c minus c. It'll cancel out later on, right? So we don't need it. For definite integrals, you never have a plus c. And there's only one answer, right? It's representing a sort of an area as opposed to a family of functions. Okay, so first things first, what is the square root of 1 minus cosine squared alpha? Well, 1 minus cosine squared alpha is sine squared alpha, right? Because sine squared alpha plus cosine squared alpha is 1. That's a famous identity, Pythagorean identity. And so this is just the square root of sine squared alpha, which is technically the mod of sine alpha. But again, if we think about our sort of region here from 0 to pi, that is going to be sine alpha is always going to be positive there, right? It's going to go to 0 to 1, then back to 0. So we don't need that mod, right? We can just treat that as sine alpha by itself. And with this question in general, I am not going to be dealing with any weird mod stuff going on. They might sometimes trick you up with stuff like that, or trip you up with that kind of thing. But here, you can, because of the sort of region they've given us, things work out particularly nicely, which is good. So I can just say this is going to be over sine alpha, so that's going to be over sine alpha. And similarly over here, I can replace this square root 1 minus cosine squared alpha with sine alpha. So notice that this looks pretty similar to sort of the first part of the question. The first part of the question told us that 1 minus cosine alpha over sine alpha is equal to tan of alpha over 2. So this isn't quite in that form because I have an x there. I don't really know what's going to happen if I turn this into an x. But remember, this is just, we're evaluating this, right? At x equals 0 and x equals 1. So let's just do that, right? So what's this going to be? It's going to be, if I just sort of evaluate it, I'm going to get this is equal to sine alpha multiplied by 1 over sine alpha arctan of 1 minus cosine alpha over sine alpha, right? Because I'm just plugging in x is equal to 1. To evaluate it at 1, that's what I have to do, right? And then I minus from that 1 over sine alpha arctan of 0 minus cosine alpha, so that's just going to be minus cosine alpha over sine alpha, right? So this is really what I get when I evaluate that. I realize I've slightly gone off screen here, but that's what I get when I evaluate sort of that big sort of mess right there that I get when I sort of do that integral. And we immediately notice this, right? 1 minus cosine alpha over sine alpha. We know that, right? That's tan of alpha over 2. So we can just replace this with tan of alpha over 2. So this just gives you arctan of tan of alpha over 2. Right? And so between 0 and pi, this is always going to give us alpha over 2, right? Arctan of tan of something, right? Arctan and tan are inverse functions, so they're going to sort of cancel each other out and just give us alpha over 2, right? So we just get 1 over sine alpha multiplied by alpha over 2, and then we have, so then we just write minus 1 over sine alpha minus 1 over sine alpha arctan of minus cosine alpha over sine alpha. Okay, so that's slightly trickier, the second part here, right? Well, what is this? What's arctan of minus cosine alpha over sine alpha? Well, it's arctan of minus cot alpha, right? Now, we're going to need to be a little bit smarter at how we treat this. Well, arctan of, well, first of all, arctan of minus x is going to equal minus arctan of x. And this is because arctan is an odd function, which means effectively that f, if I have any function that's odd, it means that f of minus x is equal to minus f of x. And the reason I know that is because arctan looks a little bit like this, right? It's going to go from sort of minus pi over 2 to pi over 2, right? And it sort of has this sort of horizontal asymptote, right? As x goes to infinity, it's going to sort of asymptote at pi over 2. But namely, if I plug in a value of x, say it's positive over here, and I evaluate that, I'm going to get some f of x, which is like sort of this point here. But also if I evaluate the function at sort of the negative of that value, so somewhere over here, then what I get is a point down over here, right? Which is actually, as you can see, just the negative of what I get up here, right? In other words, it's symmetric about the origin. Now that isn't particularly rigorous, but you can make it rigorous, and I guess I'll leave it as an exercise to think about how you could do that. But effectively, you can see that that's true just by looking at the graph. So I guess if we have that piece of information, then we can write arctan of minus cot alpha as minus arctan of, so that's going to be minus arctan of cot alpha. This still isn't good enough though, but what I do know is, well, one piece of information that's very useful in general, linking cot and tan, is as follows. So cot alpha in general is equal to tan, right, of pi over 2 minus alpha, right? So what does this mean? Well, again, if you look at their graphs, in fact, I might just do this. I might just get up Desmos for this. It's best described by Desmos. So let's have a look at tan x, right? Tan x looks something like that. And if I do tan of minus, so I'm going to do tan of x, and then tan of minus x. So what's that doing? That's reflecting my initial sort of red function tan x in the line in the line x equals 0, right? So just the y-axis, it's reflecting that initial function in the along the y-axis to give me that blue function there. And then what am I going to do? Well, I'm going to do tan of pi over 2 minus x. Well, what is that going to be doing? That's just going to be adding pi over 2 to the input here. So that's going to be adding pi over 2. And what has that done? Well, if I go back and get tan minus x here, that shifted it, right? That shifted it to the left by pi over 2. And these are transformations that you should be familiar with from GCSE. So if I just look at tan of minus x plus pi over 2, that just represents my tan x reflected and then shifted. And what happens then if I graph my cotangent of x? You can see that that is actually the exact same as my tan x reflected and flipped. So that's a cool way of showing that to be true. Is there another way of showing that to be true? Again, have a think. But that's some intuition for you as to why that's true. And we can use that in these questions to help us out. So we have that sort of result there. And so if we have that result, then what we realize is that then basically what we have to evaluate is minus arctan of tan of pi over 2 minus alpha, right? Again, this is nice. This is what we want, because arctan and tan are inverse functions. So arctan of tan of pi over 2 minus alpha is just pi over 2 minus alpha. So effectively this here is just going to be equal to minus pi over 2 minus alpha. So no more trig functions in there, which is good. So if I clean up what I had in the line above, then this just becomes multiplied by minus pi over 2 minus alpha. And these two minuses can combine to make a plus. So I can just get rid of them both, right? It gives me plus, right? 1 over sine alpha times pi over 2 minus alpha. So now we're in a position to evaluate this, right? So this just gives us, so sine of alpha times 1 over sine alpha is just 1. So we can clean that up. That gives us alpha over 2 plus, again, sine alpha times 1 over sine alpha is just 1. So plus pi over 2 minus alpha, which just gives us pi over 2. So alpha over 2 minus alpha just gives us minus alpha over 2. So minus alpha over 2, which is just the exact same thing as a half times pi minus alpha, exactly as required. Difficult question, that. I think the hardest part really is evaluating that arctan of minus cot alpha. This is what came to my mind because I just knew these facts, but maybe there's another way to do it. What do you guys think? Let me know in the comments if you have a better way of doing it. Of course, kindly. And thank you very much for watching. I'll see you guys in the next one.